We will now have a look at the so-called shift method that takes a planar graph and its canonical order and lays out the graph in this order. This, of course, works inductively, so we want to keep up some drawing invariants. Namely, we want to make sure at every step that our graph gk-1 is drawn such that v1 lies exactly at the origin and v2 lies exactly at coordinate 2k-6 and y coordinate 0. So it's drawn as a horizontal segment here. The boundary of the graph gk-1 minus this edge is drawn x monotone, so we don't go to the right and backwards. And even more strongly, every edge here is drawn with slope plus or minus 1. So this is how the boundary of gk-1 could look like. So let's assume that we have a drawing of gk-1 where all these conditions hold. Now we want to place our new vertex vk. We have the leftmost neighbor wp and the rightmost neighbor wq. We have to make sure that these conditions still hold. So the only way to create an edge between wp and vk and an edge from vk to wq is by making the slope plus 1 here and minus 1 here. So we have to place the vertex at this position. But now this is a problem, because here we have overlaps, so the drawing is not planar anymore. But the good thing is, if we go from gk-1 to gk, then because of this we get 2 more x coordinates, so we can still move things around. So what would be your solution for this case here? What we can do is we can create 2 cuts here between the leftmost neighbor and its neighbor and between the rightmost neighbor and its neighbor. And now we move all the vertices that lie to the left of this 1 coordinate to the left, and all the vertices that lie to the right of this 1 coordinate to the right, like this. And now if we connect these, then things seem to work out. We still have to prove that, but it looks much better than before. Well, one more thing we have to fix is we moved all the stuff 1 to the left, so now this would be at -1, 0, but we can just move the whole graph 1 to the right again, and then this condition clearly holds, this condition here clearly holds, and this condition here also holds. But can we even place vk on this position? So is this a grid position? Or could it be that we have the case like this, that it lies somewhere in the middle between grid lines, or on a grid line but not on a horizontal grid line? But we can show that it really does land on a grid line. And that comes from this condition here. And for that we want to have a look at the so-called Manhattan distance between x and y. That's just the sum of the x distance and the y distance here. And from the slopes, it follows that these 2 vertices always have an even Manhattan distance. So if we move from this vertex up to here, and we just follow these segments, in every step it has slope plus 1 or minus 1. So we go the same number of coordinates to the right as we go upwards. Same to right and upwards, same right and upwards. So between any pair of consecutive vertices on the boundary, we always go the same distance in the y coordinate and the same distance in the x coordinate. So every pair of these have an even Manhattan distance. Means we have even from here to here, here to here, here to here, and so on, until we get to wq. And since all the distances were even, the distance is also even between wp and wq. That means before the stretching here, the intersection of the lines of slope plus 1 and minus 1 through these 2 vertices is on a grid line. And now we move this 1 more to the left, this 1 more to the right, so their Manhattan distance increases by 2. And that means that it is still even. One very important thing we haven't proven yet is that what we are doing here still gives us a planar drawing. But before we do that, we want to have a look at one example to get a feel for it. And for that, we will mark this part in the middle and call it L of vk. And when we do our shift, instead of moving to the left and right, we will just move everything inside here 1 to the right and everything inside here 2 to the right. So let's have a look at our example that we had earlier. All the vertices will always lie on such a triangle grid. We will never reach the coordinates up here or up here. We can easily start by using G3 and placing the vertex 1 here, 2 here and 3 here. Now if we go to G4, we have to make sure that 1 is at the origin, that's fine, and 2 is at 2k minus 6, so 2 times 4 minus 6, which is a 2, so it works out. So let's have a look at the next vertex 4. It has 2 neighbors, 3 and 2, which are these 2 here. Now we first have to move according to this diagram here. So this vertex lies on the first part, it doesn't get moved. This vertex lies in the third part, so it gets moved 2 to the right. And now we place the new vertex on the intersection of these diagonals, so here, and we have our drawing G4. Go to G5, again we have these 2 neighbors on the orthoface. This one lies here, so everything to the left of it also does not get moved. This one gets moved by 2 to the right, and we place it on the intersection. For the next vertex, this here, it's exactly the same, and also for 7, 8 and 9, nothing more interesting happens. But now we get to vertex number 10. It has 2 extreme neighbors 9 and 4, but also the neighbors 8, 7 and 3 in between. So these neighbors lie in this part. Means the orange ones here get moved by 1, and everything here to the right will get moved by 2. And again, we can place it at the intersection. And this here is our L of 10. Let's have a look at 11. Here we have one vertex that gets moved by 1, everything here gets moved by 2, everything here gets not moved at all. And 12, it's again simple. At 13 we have one neighbor in the middle, which is number 4, which lies here, so this here is L of 13. And now we get to a more interesting case, number 14. We have 13 here, so this is our left part, we have 6 here, so this is the right part, and we have L of 14 here. And now for the first time we have some interior vertex here in L of 14. But this is reachable by an edge that also completely lies inside this area from some vertex of the orthoface. Let's see if that always holds. With 15, this is our area L of 15. We have some interior vertices. They all are connected to this guy on the orthoface. And finally for 16, now it gets a bit larger, but this is our area L of 16. This one is connected to this one. This one is connected here. This one is connected here. These don't have a direct connection, but they are connected to this one, which goes up here. So we can basically have some trees that contain all the vertices of this area. Now that we have looked at the example, how can we prove that what we're doing here gives us a planar drawing? So let's assume that we have the graph gk-1 and we add the new vertex bk on the orthoface. And in gk-1 we have all these w's here, w1, the left neighbor wp, wp plus 1 and so on. There are a bunch of vertices that were on the orthoface before but are not on the orthoface now. Those we call the covered vertices. And exactly as in the proof for the running time of the canonical ordering, this only happens when, if you go back, it gets to the orthoface. Now it's removed from the orthoface. That can only happen exactly once. So every vertex is covered exactly once. Now if you look at the relation between the vertices, vk covers these vertices here. These might cover other vertices here. But every vertex is covered once, so every vertex basically has one incoming edge. So this covering relation defines a tree in our graph. And in the subgraphs here, it's a forest, like this. This vertex covers this here, and this might cover others here, but this one here is not covered by vk, so we have a bunch of different trees, and a bunch of trees is a forest. Now what do we have to do to make sure that our drawing is planar? After we do this cut, we we have to make sure that 1, the new edges don't cross anything that was there before, and 2, that what was there before is still drawn planar. For the first step, what about the new edges? Those are clearly planar, because if you look at this step here, these edges now have slope plus minus 1. This one was plus 1 before, but it was moved away, so we cannot have a crossing here. This one was minus 1, but it got moved away, so we cannot have a crossing here. And all the other edges inside, they have a larger slope. They are either larger than plus 1 or smaller than minus 1. So there cannot be anything else sticking into them. So here we cannot have any crossings. But what about the gk-1 part after shifting? For that, we want to use a broad lemma. So we want to look at all these covering sets, which are exactly our L sets that we defined before, and we want to prove that we can shift those in some way, and then everything still remains planar. So we want to prove the following theorem. Suppose that we have a planar drawing of our graph GK. So of this whole thing here. Now we find some variables, delta 1 to delta t. And they are non-decreasing. So delta 1 is at least 0, delta 2 is at least 1, delta 3 is at least 2, and so on. Now if we take all these L sets and we shift each of them by delta I to the right, then the drawing remains planar. So we shift this one by 0, for example, then W2 and it's set by 1, then this and it's set by 1, this and it's set by 2, Vk and all of these by 3, this here by 4, this by 4, this by 4, this by 4, for example, then it's planar. In our inductive step, we will only do this for 0s, 1s, and 2s, but we need the general form for the inductive proof. So how do we prove this? In the beginning, when we only have G3, then it's very clear. We have exactly 3 sets, so as long as we move them in this way, everything is still planar. So we can inductively assume that for gk-1, this holds. And now we want to prove that if this lemma holds for gk-1, it also holds for gk. And how does this work? Well, if for gk we get a number for all these vertices on the orthophase, then we can apply a shift to gk-1. So we want to shift all these vertices in the drawing of gk-1 by exactly this number. We want to shift all these by exactly this number. And we want to shift all of these by the number we got for vk. By induction, this is still a planar drawing. But now what about gk? Well, we applied the shift all here, and it only remains to move vk to the right as well. But we move it rigidly with everything that's down here, so this subpart of the drawing doesn't change at all. It means we cannot get any new crossings here. And for these two edges, well, they are still clearly outside of this whole drawing, so the whole thing remains planar. And then, since we have this lemma, that means that we can apply our shifts at every step and we don't create any new crossings, and so the whole method gives us a planar drawing. And in the final part, we want to figure out what is the runtime of this algorithm.